Hello everyone. Today we are talking about sections 1 through 4 in chapter 8. So the first section we discuss chemical bond formation and Lewis electron dot structures. So chemists think of bonds as falling into three broad categories, metallic, covalent, and ionic. We will discuss metallic bonding in chapter 12, so that will be next semester in Chem 102. So in this semester, we will concentrate on covalent and ionic bonding. But keep in mind that boundaries between these types are indistinct. There's not a sharp line between what's a covalent bond and what's an ionic bond. So first, let's talk about covalent bonds. So covalent bonds involve sharing of electrons from each other's outermost shells. So in this example, we see that it's the valence electrons and not the core electrons that are shared. And that is why when we were talking about electron configurations, we were always careful to write them in terms of the noble gas structure. So we can see that if we write the electron configuration for chlorine, it's neon plus 3s2, 3p5. So chlorine has 7 valence electrons. So we can draw the 7 electrons around chlorine, and we can pair up all of them except for one. So the reason that we have Cl2 coming together is that both of these unpaired electrons will come together and they will form a bond. So a bond is defined as 2 electrons, and in this case, the 2 chlorine atoms are sharing those 2 electrons. So let's talk about ionic bonding now. So ionic bonds involve the transfer of valence electrons. So again, covalent bonds was sharing of electrons. Ionic bonds involve transfer of valence electrons. So if we draw the electron configuration of sodium, we would find that it's neon plus 1 valence electron. So that's drawn over here with a single valence electron. And for chlorine, we showed that in the previous slide where it was neon plus the 7 electrons, 3s2, 3p5. But if sodium loses its electron, and if it transfers its electron to chlorine, then sodium becomes a positively charged ion, and now its electron configuration is the same as that of neon. So we saw that in the last chapter. And if chlorine gains an electron to become chloride, now its electron configuration is that of argon. So we have these very stable ions, both of them have noble gas electron configurations. So now we have a sodium plus and a chloride minus, and they are now attracted to each other by these electrostatic attractions. So here we have an electron transfer, we have an ionic compound, and remember we learned at the beginning of the semester that the metals will lose electrons and the non-metals will gain, and we see that in this example. So we can look at chemical bonding via this Van Arkel-Ketelaar diagram, and this shows the 4 regions of bonding. So metallic is shown in blue, semiconducting in green, ionic in sort of a reddish orange, and covalent in yellow. So again, we will not be focusing on metallic or semiconducting bonding in this course, but we will be talking about ionic and covalent bonding. And if you look at where the ionic and covalent bonding is, first if we look at ionic, you can see that on the y-axis we have the difference in electronegativity is going up. So with these ionic compounds right here, these are largely formed from metals and nonmetals because the difference in electronegativity is very great between the two of them. So with covalent bonds, the covalent bonds are made of nonmetals, and mostly they involve sharing of electrons. But again, notice there's kind of a blur here. Sometimes we have bonds that aren't purely ionic or purely covalent. So the Lewis symbols for atoms, we can draw a Lewis electron dot structure just for atoms. And if you look down in this table right here, we show that for the 1As, we have 1 valence electron, and 2 have 2, 3 have 3, etc. And what we do is we draw these Lewis symbols, and a symbol shows just the valence electrons, and it shows the electrons as being dots. So each of these dots show the number of valence electrons that we have for each of these atoms. So what we do is we draw the electrons singly, and then we don't start pairing them up until we get over 4. So when we get to the 5A, we can see that we have nitrogen with 5 valence electrons, so we pair them up until we get to the noble gases, and now we have 8 valence electrons, and we have 4 pairs of electrons. So the noble gases show us that we can have elements that gain or lose or share electrons to achieve an octet of valence electrons, because that's what the noble gases have. So we know that the noble gases are unreactive, so that must be very stable. So this is referred to as the octet rule. So now what we can do is we can go to the next section and we can look at covalent bonding and Lewis structures, and we can see how we can take atoms and put them together to form compounds. So we're focusing on covalent bonding now. So molecules and polyatomic ions that participate in covalent bondings are all nonmetals. So when you see a molecule or a polyatomic ion that's composed of nonmetals, they are attached to each other via these covalent bonds. And again, the thing to remember is that the bonds and the electrons that make up the bonds in covalently bonded compounds are shared. So when we say bond, a bond is an electron pair. So an electron pair is 2 electrons. So when we say we have a bond between 2 atoms, it's 2 electrons. So we can start with drawing Lewis structures for H2 hydrogen, so that's the very simplest one. So each hydrogen has 1 valence electron. So if this hydrogen has this valence electron and that hydrogen had that valence electron, then the 2 of them come together to form a bond. So there's a bond between these 2 hydrogen atoms. So that means that those 2 electrons are shared. So we could just draw the 2 dots, but usually what we do is we draw a line. And when you see a line, that's a bond, and the line means 2 electrons, and it means that the electrons are shared. So how about F2? Okay, so fluorine has 7 valence electrons, so that's drawn down here. And we have the 7 valence electrons, and then we have each one of these electrons that is unpaired. But if they get together, then the 2 fluorine atoms can share those 2 electrons and form a bond between them. So now we have, in fluorine, we have a shared or a bonding electron pair, but surrounding each of the fluorine atoms, we have non-bonding pairs. So those electron pairs are important for fulfilling the octet rule, but they aren't involved in the bonding. So we can also write Lewis structures for carbon dioxide and nitrogen, and we can see from the carbon dioxide that we have a double bond, so we have 2 pairs or 4 electrons that are being shared. And this fulfills the octet rule. If I draw a little circle here around the oxygen, and I draw another circle around the carbon like this, where my circles overlap, that's where the electrons are shared. So oxygen has 2 lone pairs of electrons and then 2 pairs of electrons that are shared with the carbon. So both of those oxygens look like that, whereas the carbon has no lone pairs, no non-bonding pairs. It is sharing all 8 of its electrons in 2 bonds with each oxygen. Nitrogen forms a triple bond. So if I look at this nitrogen, if I draw a circle around here, another circle around here, then you can see where my circles overlap. There are 3 bonds, so that's 6 total electrons that are shared. So in the nitrogen, there are 6 electrons that are shared, and then 2 electrons on each nitrogen that are non-bonding pairs. So that fulfills the octet rule. So what we want to do is we want to go through the steps of how to draw a Lewis structure. So we're going to use CHCl3 as an example. So the first step is to determine the arrangement of atoms within a molecule. So sometimes the way that the formula is written can give you a clue about that. Often the central atom, which is being pointed to right here, often the central atom is written first. So that can be a clue as to how I should arrange the the atoms, how they're bonded to each other. We'll also learn that the central atom is usually the one with the lowest affinity for electrons, and we talked about electron affinity in the last chapter. We'll talk about electronegativity in section 8.7, but you might remember a while back when we did our molecular bonding exercise, we talked about electronegativity back then. So the next thing we should do is we should determine the number of valence electrons. So there we use our periodic table, and we find that carbon has 4 valence electrons and hydrogen has 1. We have 3 chlorines, each with 7 valence electrons. So we add this up, and we have a total of 26 electrons that will be in 13 pairs. So whatever structure we draw, we want to make sure it has 26 electrons. So now what we'll do is we'll take our central atom, so we determined that carbon was the central atom, and then we'll draw single bonds to each one of these atoms. And we'll find when we do a lot of these things that we'll find that carbon likes to form 4 bonds. So we'll put carbon in the middle, and we'll put 4 bonds, 1 to the hydrogen and 1 to each of the chlorines. So those are bonds, and a bond consists of 2 electrons. So I've got 2, 4, 6, 8 total electrons. So that's 4 pairs of the 13 pairs that we know exist in this molecule. So what we do now then is we draw dots, or these non-binding electrons, around each of the atoms. But we don't do this for hydrogen, because hydrogen only has 2 electrons. So that's an exception to the octet rule. So if I put pairs around each chlorine, I've got 2 here and 2 here. So if I count, I've got 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. So there are all of my 26 electrons. And if I draw circles around here, I can show that I have obeyed the octet rule around each atom except for hydrogen. So I'll draw some more circles around the carbon, and you can see where my circles overlap. That's where the electrons are being shared. So I'll go ahead and shade those like that. So each atom in this molecule is surrounded by 8 electrons. So in the case of the chlorine, 6 of the electrons are associated just with chlorine itself, whereas 2 of the electrons are shared. Whereas for the carbon, all 8 of the electrons that surround the carbon, they are all shared. So the next step in how to draw Lewis structures would involve, if you got to 26 electrons, that was the number of valence electrons we had, and then you found that your central atom or one of your atoms didn't have an octet, then you might be in the position of having to draw some double bonds. But that's not true for the CHCl3. So we have a completed Lewis structure here. We drew a structure with the central atom of carbon. We obeyed the octet rule around every atom except for hydrogen, and we have a total of 26 valence electrons. So in our book we have an example. So our next example is, let's draw a Lewis structure for thionyl chloride. It's SOCl2, and let's follow these steps. So first, let's determine the arrangement, and again, the one with the lowest affinity for electrons will be the sulfur. Also, it's drawn SOCl2, and usually the central atom is drawn first, not always, but often. So we can put the sulfur in the middle, and we can draw a bond to oxygen and bonds to chlorine. Step 2 is to figure out the number of valence electrons. So we have sulfur has 6, and oxygen has 6, and chlorine has 7, and we have 2 chlorines. If we take 6 plus 6 plus 14, we get 26, and that's 13 pairs. So now we're going to do the same thing that we did for CHCl3. We'll put 1 pair of electrons between the bonded atoms to form a single bond. And if we do that, we get something that looks like this. And then what we do is we write electrons around each one of the chlorines. So now I've got 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. So I don't have 26 yet. So what I need to do is the other 2 electrons are going to go right here on the sulfur. And that means I can obey my octet rule. So again, if I put a circle around here, and a circle around here, and a circle around here. And now I'm going to put circles around my sulfurs, and again, where I've overlapped my circles, that's where the electrons are shared. Then I can see that I've obeyed the octet rule around each one of the atoms. So each of the chlorines and the oxygen has one bond to sulfur, and then 3 pairs of non-bonding electrons around it. The sulfur has 3 bonds, or 6 electrons that are shared, and 2 non-bonding electrons. So we don't have to do step 5 either, because here we have obeyed the octet rule around all of our atoms, so we don't need to draw any double bonds for this structure. So let's do another example. Let's do formaldehyde. So formaldehyde has the formula CH2O. So if we determine the arrangement, again, carbon is in the middle, and we have single bonds to hydrogen, and then we have a single bond to oxygen. Then we determine the number of valence electrons. So carbon has 4, hydrogen has 1, and we have 2 of them, and oxygen has 6. So we add that up, we get 12 electrons total, or 6 electron pairs. So if we draw our structure like this, we've got 2, 4, 6, so we don't have all of our 12 yet. So if we do step 3, where we put electrons to form the single bonds, we've already done that. If we do step 4, if we then add the lone pairs around oxygen, because remember hydrogen only has 2, then if we add this up, we have 2, 4, 6, 8, 10, 12. So we have 12 electrons total, but you might notice that we haven't obeyed the octet rule around carbon. We have around oxygen, but not around carbon. So step 5, we are told that maybe we're going to have to move something. So we can take this pair right here and we can move it, and now we have a double bond. So we have single bonds with hydrogen. You're not ever going to see double bonds with hydrogen, so don't move them there. But we have a double bond. We have 2 shared pairs of electrons. So now you can see that we've obeyed the octet rule around oxygen, and we've obeyed the octet rule around carbon. And carbon and oxygen share 2 electron pairs, or 4 total electrons between them, and that constitutes a double bond. So if we look in our book, there's a strategy map in our book, and it talks about what if I wanted to draw the structure of chlorate, which is ClO3-. Now that is a polyatomic ion that we learned about at the beginning of the class. So if we do our steps here, decide on a central atom. Well, if we're given ClO3-, again, that gives us a clue as to the central atom because the Cl is drawn first. And then we have to calculate the number of valence electrons. So we have 3 oxygens, and oxygen has 6 valence electrons, so that's 18. Chlorine has 7, so that's 25. Now remember, we're drawing, this is ClO3-. It has an overall negative charge, so we have to add an extra electron. So we get 26 total. So now what we do is we carry out the next steps where we draw these lone pairs around all of the oxygens. And if we do that, you can see we have 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, and then we put the 26 down here on the chlorine. And that way, we have fulfilled the octet rule around each of these atoms, as I'm drawing my circles right here. And the oxygen is sharing 2 electrons with each oxygen is sharing with the chlorine. And the chlorine has 1 pair of non-bonding electrons, and the oxygens each have 3. Now, if we're going to draw an ion, the convention is to put brackets around the ion and then to write the charge outside the brackets. So this was chlorate, which was ClO3-. So we would write the brackets and then write a minus charge on the outside of the bracket. So in terms of trying to figure out what the central atom is, our book authors gives us some tips. So again, we're going to use the one with the lowest electronegativity. For simple compounds and ions, it's often the first atom in the formula. Certain elements appear often as central elements, like carbon, nitrogen, phosphorus, and sulfur. Halogens are often, not always, but they're often terminal atoms forming a single bond, but they can be the central atom. In fact, we just drew the chlorate where we saw that chlorine was the central atom. Oxygen is the central atom in water, but in combination with these other elements, nitrogen, phosphorus, and halogen is usually a terminal atom. And with rare exceptions, hydrogen is a terminal atom because it bonds to only one other atom. In fact, I won't give you any examples where we have these rare exceptions. So hydrogen will be a terminal atom and it bonds to only one other atom. So again, trying to predict the Lewis structures, carbon, nitrogen, and oxygen are typically central atoms and halogens are typically terminal atoms. But there's often a pattern, not always, but there's often a pattern. This is shown for period 2, but period 3 often follows this pattern too. Or for group 4A, you'll see the central atom has 4 bonds around the central atom. For nitrogen, we show 3 bonds and a non-bonding pair. Oxygen is often 2 bonds and 2 non-bonding pairs, whereas the halogens are often 1 bond and 3 non-bonding pairs. Now that's not 100% of the time, but this is often a pattern that we see. And for the elements in period 3, we often see that as well. So our book authors give us some examples of compounds that obey this formula. So in group 4A, you can see that methane, ethane, ethylene, and acetylene all have carbons with 4 bonds. Sometimes the bonds are single bonds, as we see here, and that could be either double bonds or triple bonds. The ammonia, same thing, 3 bonds and 1 lone pair, and we see that with ammonia and hydrazine, and the ammonium ion and the amide ion right here also follows that pattern. Actually, no, amide doesn't. We have got 2 lone pairs and 2 bonds. The ammonium ion has 4 bonds and no lone pairs, so we don't always follow the pattern. Water, we have oxygen, 2 bonds, 2 lone pairs, but here are some exceptions down here where the hydronium ion has 3 bonds and a lone pair, and the hydroxide has 1 bond and 3 lone pairs. And here's hydrogen fluoride, where we typically have 1 bond and 3 lone pairs. So let's talk about something called formal charge. I have a video posted on Sakai that shows a simple way to do this, and I'm going to show you the same way as the video. I think the way the book does this is a little difficult. I think my way is easier. So individual atoms can have either negative or positive charges, or sometimes they don't have a charge, but sometimes they do. So this tells us the electrostatic charge that would reside on an atom in a molecule or an ion. So if we for an example, let's go back to the chlorate. So what are the formal charges in this polyatomic ion? Well, the way that we do this is, I'm just going to draw my circles again. So I have oxygen, and here what I'm going to do is I'm actually going to split up my electrons. So I'm going to do this a little differently, where if I have a shared electron, I'm going to give 1 to the oxygen and 1 to the chlorine. So here I'm not going to draw overlaps. So I'm going to do this. So if we count, if I look at the oxygens, I can have 1, 2, 3, 4, 5, 6, and there's the 7th one. One of the electrons it shares with chlorine. And all of the oxygens look like that. So again, 1, 2, 3, 4, 5, 6, 7. And this oxygen looks the same way. 1, 2, 3, 4, 5, 6, 7. Chlorine has 1, 2, and then let's look at the shared ones, 3, 4, 5. So each of the oxygens, if we take the shared electrons and divide them evenly, each of the oxygens have 7 electrons, and the chlorine has 5. Well, we know that oxygen normally has 6 valence electrons, so if you give it an extra, 6 minus 7 gives us a minus 1. So that means that all of these oxygens have a minus 1 formal charge. We also know that chlorine normally has 7 electrons, so if it only has 5, then we can take 7 minus 5, and that gives us plus 2. Now overall, this has to be minus 1. Remember, this is chlorate, ClO3 minus, so we have to have a negative charge overall, but we do. So if we have minus 1, minus 1, minus 1 for each of the oxygens and plus 2 for the chlorine, that adds up to a minus 1 charge. typically, the way that we do this, if it's -1, we just write a negative charge. So we have a -1 here and a -1 here, so we just write negative. So we have a total of 3 negative charges and a +2, and that adds up to -1. All right, so the next concept we want to go through is something called resonance. So you might notice when you're drawing electron dot structures that you might be able to draw 2 different structures. So ozone is O3, and it looks like this. And I can draw it with a central oxygen, and I can draw it with a double bond over here on the left and a single bond on the right. Or I can draw it with a double bond on the right and a single bond on the left. But that makes it seem like they're not equivalent. And actually, there are ways that we can measure these things. Ozone actually has an angular or bench geometry. We'll talk about why in the next section. But you can measure these distances, and they are identical. So between this oxygen and this oxygen, the distance is 127.8 picometers, and the same thing over here. This is also 127.8 picometers. So what we need to do is we need to draw a structure where those bonds are equal. We can't really do that with the rules that we just talked about. So what we end up doing is we draw 2 structures. So if we just draw one Lewis structure, it doesn't really accurately represent what this molecule looks like. So what we do is we draw it like what's shown on the bottom. We show that we have the structure on the left, where I show a single bond on the left and a double bond on the right. And then I show another structure where I put the double bond on the left and the single bond on the right. And then we have a resonance arrow between the 2 of them. This is not an equilibrium arrow. It doesn't mean that this molecule is shifting back and forth. What it means is that we can't really draw a structure that accurately represents the molecule. We can't draw a single structure. So what we're going to do is we're going to draw 2. And we're going to say that the real structure of ozone is a mixture or a hybrid of those 2. So we have to draw the 2 resonance contributors to this hybrid or this mixed structure. Notice when we do that, the connectivity is the same. So I have all of the oxygens are in a row in both structures, and the only thing I moved around was the electrons. So as another example, this is from our textbook. So this is the nitrite ion. So if we do the same kind of thing where we figure out, okay, what's the central atom? What's nitrogen? That's the least electronegative of the 2, nitrogen and oxygen. Plus the way it's written gives us a clue that nitrogen's in the middle. And we have 2 oxygens, each with 6 valence electrons, and a nitrogen with 5, and again, this is nitrite NO2 minus, so I have to add an extra electron. So I have 18 valence electrons, and I can draw 2 structures again. One has a double bond on the left, and one has a double bond on the right. But again, we can go into the lab and we can make these measurements, and we find out that that's not really what it looks like. The bonds between the nitrogen and each of the oxygens are equivalent. So we have to write 2 resonance contributors. So the actual structure of the nitrite is a hybrid between these 2. So again, these are ions, so we're going to draw the little brackets around here plus the negative charge on the outside of the bracket, and we'll draw this arrow in between to indicate that these are 2 resonance contributors, that each one of them contributes to the actual hybrid structure of this ion. So I want to go back to this strategy map and this chlorite ion that we drew the structure of. So technically we followed all the rules and we did what we were supposed to, but it's not really the best structure of all the structures we can draw. So it is true we drew a structure, it had 26 electrons, and we obeyed the octet rule, but we also calculated the formal charge, and we found out that chlorine had a +2 formal charge, and each of the oxygens had a -1. Well, I went through and I drew 3 more structures, and in each one of these, the chlorine is still in the middle, but here I drew a double bond between this oxygen with only 2 lone pairs. Here I drew a double bond on this oxygen And here I drew a double bond on this oxygen. And if I do the formal charge, so you can do this on your own, but if I do the formal charge, this oxygen has a formal charge of -1, and so does that. And then the chlorine here is +1. So I have -1, -1, +1. That adds up to be -1. Same thing over here. The chlorine's +1. And this is -1, and that's -1. And that adds up to -1. Same thing over here. This is -1, that's -1, and that's +1. So the imbalance of charge is a little less than the structures that I drew down here. So the chlorine is +1 and not +2. And plus, in these structures here, I do have one atom. So this oxygen right here, these oxygens that are doubly bonded, don't have any formal charge at all. So these structures will contribute more to the hybrid structure. So what we should really do if someone asks us to draw a structure of chlorate is you should really draw all four. But these three structures right here are going to contribute more to the actual hybrid structure. When you're mixing these together, the mixing won't be equal. And the structure way over here on the left will contribute less because of this imbalance of formal charge. So again, all of these ions are drawn with brackets around them and with the overall charge written on the outside of the bracket, and with these little resonance arrows in between. So you should test your knowledge by doing these problems in the back of the book, and I will talk to you next time.